Classmates, how's it going? My name is Andre Williams, and my term project was based on class rarity in big data, or otherwise known as classifying imbalanced data. Before I continue, I want to say it's been an honor to learn such fascinating material with such a good group of students at such a historic time. Let's continue. All right. An empirical study on class rarity in big data was the research paper that was assigned to me. It was basically a case study to prove that the more imbalanced your data set is, the more it will degrade the performance of your classifier. The three authors are listed below. Okay, what is data rarity? What are the issues? Let's see. Data rarity refers to classification tasks where the classes are not represented equally. So in a binary classifier, you want your data to be distributed just so it makes it easier for your model to learn. Imbalanced data could create a bias, and we all know we don't want to introduce any type of bias in our predictors. Um, and then finally, imbalanced data is more prevalent as big data and rarity goes hand in hand. Now, in this profession, once we get out in the field, data rarity is going to be quite common, especially when you think of situations like uh, fraudulent visa transactions. There's probably tens of millions of visa transactions every day, and you might have a handful of fraud cases. So that's something to consider. Okay, the experiment done in my research paper was based on detecting fraudulent activity in the Medicare system. So using the Medicare data set, they extracted 1,400 positive cases out of 3,962,555 total instances. So that's pretty imbalanced. And then they randomly removed data points out of they randomly removed instances out of the data set to make your class more to further imbalance your data even more. You can see it gets worse as we progress down. And here is the results after we did a 5 satisfied cross-fold validation. Um, you can see the results of the area under curve. The performance is it gets worse as we remove more and more data points out of our data set. Okay, so here are the results from the experiment done in my research paper. And as you can see, there's a lot of variance in the performance. It grows with increasing variety or increasing imbalanced data. There's just not enough data to discriminate between classes to make an accurate predictor here. Now, what are some techniques that have been used to mitigate class rarity? Now we have the uh, three main techniques that are used in the field. There's the first technique is on the data level. That's an external pre-processing step where you resolve the class rarity on the in the data. Uh, yeah, going forward, the second technique is on the algorithmic level. So that's basically using different algorithms, figuring out which one can compensate the most for imbalanced data. And three, um, the third technique is a hybrid. It's a combination of both methods. So on the data level approach, there's three different types of ways that you can resample the data so that it can have more of a balanced data set. The first set is a oversampling with replacing. So with oversampling is just taking your minority class and just reusing it, recycling it, replacing it over and over again to where you have an equal data set. Uh, so just to, for example, if you have 1,000 cases in class A and 100 in class B, then you would just recycle those 100 cases over and over in your minority class until you get 1,000 and 1,000 in both classes. Now that's if you wanted a 50-50 ratio. You can always change that up to do like a uh, 60-40, 70-30, whatever tickles your fancy. So undersampling is you're basically removing data points out of um, your majority class so that you can have a more balanced data set. So if you have 1,000 in class A and 100 in class B, you're basically removing 900 data points out of class A so you can get 100 and 100. Uh, to generating synthetic samples, an example of this is smoke. That's synthetic minority oversampling technique. So it's basically using a k nearest neighbor approach where you select one sample and then you find your nearest neighbors and you generate synthetic samples based on that. We'll get into that later. Algorithmic level, there's there's an two main. Well, there's plenty of other models you can use, but the ones that we used for this paper were the ensemble based. We've talked about that plenty of times in class. We'll go on this. We go into this in more details later. And there's a cost sensitive method, to basically where you're minimizing your misclassification rate by assigning a penalty to every time you have a misclassification. So if you have 1,000 in class A and 100 in class B. For every time it misclassifies a class B, it gets assigned a penalty, and that in turn compensates for the class rarity. The hybrid approach is a combination of both. The data level and the algorithmic level to compensate for imbalanced data. From the offline research I've been doing, as you can handle this with a combination of a data level and an algorithmic level, and you can even do a data, which basically use a combination of oversampling and undersampling to compensate for the imbalanced data. Okay, here is a graph of undersampling so you can get a visualization of how it works, how it's intended to work. So basically, you randomly sample instances out of your majority class to where you have a balanced data set. It's very critical that you randomly select instances out of your majority, because if your majority class is sorted, let's say it's sorted by age or zip code or anything of that nature, then and if you selected only the top 10, you would then introduce a bias into your data set. All right, classmates. So here's a demonstration of using your Weka tool to do pre-processing on your data. Um, Here I've used the same fit that the fit and test data that we've been using in class with the fault prone and not fault prone. Let's see. Excuse me. So it's the imbalance set right here. So, and as you can see, I've modified it a little bit so we have a 10-to-1 ratio. So the data set is highly imbalanced. This is going to give you a lot of bias here. So we have 133 not fault prone classes and 13 fault prone classes. Now, if you want to undersample this, you would apply a filter. So here's your filters. You want to do supervise, and you want to modify the instances, not the attributes. So here on resample, I actually want to do spread sample here. is your undersampling, and you can modify however you want the ratio to be. It says here the original data set. Oh my, the original data set must entirely fit in memory. This filter allows you to specify the maximum spread between the rarest and most common class. So let's say you want to do a 2-to-1 ratio. So you would click here, and here is your distribution spread. You also have the option here to add weights to your minority class. You can change your random seed here. I want to do my distribution spread to be 2. Let's do 2-to-1. So we should get what, 27 and 13 or something like that. So sample, hit apply, check your class, boom, and here you go. Advantages and disadvantages of undersampling. Well, one of the main advantages is that you improve the runtime of your model. You have less complexity with less data. But the disadvantages is you're losing quite a bit of valuable data for your model to learn from. Oversampling. Here's a visual graph explaining oversample. Here's an example. Um, as we said before, you're basically just repeating your minority class over and over again until you have more of a balanced data set. Now, here is an example of how you would want to oversample your data. Same thing. Um, you have 10-to-1 ratio, 133, and you're not fault prone, 13, and you're fault prone. So this time you will use the same directories, but you want to go to resample here. This is your oversampling. So you want to click in your filter, and you just want to set this to 1. And we should get what, like 73. So you apply, and yeah, 73 and 73. That gives you a, yeah, let's see. Oversampling advantages and disadvantages. Well, you're going to have more data, so it's more computationally expensive. And to recycle that data, I'm sure you're going to have a for loop, which is going to add to your complexity. Um, one of the advantages is there's no information loss, so you're providing more information for your algorithm to learn on. You increase likelihood of overfitting. That's a huge disadvantage. Now, how does this increase the likelihood? It's basically, to make a long story short, your model is just relearning the same data points over and over again. As you keep recycling and replacing the minority class over and over, your model is relearning, is learning so much about those data points that it won't be able to generalize well, and that's going to cause overfitting. All right, generating synthetic samples. We've discussed this earlier, and this is just a visualization of how you do this. You get a one specific data point. You find the nearest neighbors, whatever you choose, 3, 5, or 7, however many. You find a midpoint of the distance between the nearest neighbors, and whatever the midpoint is, you create a new sample there. And it doesn't have to be the midpoint. It could be 25%, 75%. There's one there's one major disadvantage that we'll talk about for this, and I'll draw it out for you. Let's say you pick these two data points as nearest neighbors. When you take the distance here, you're going to, let's say you use 25% of this distance. If you generated a synthetic sample here, right, you're going to have an overlapping of data points there. So, and that's gonna generate noise, which is going to introduce a lot of difficulty into your model. So generating synthetic sample advantages and disadvantages. It alleviates overfitting because you're generating new data points, so you're not learning the same data points over and over and over again. There's no information loss. You're not eliminating data. Can increase overlapping of classes, which introduces noise. And yeah, we've already went over that, and that disadvantage can magnify once you get into like three-dimensional data points. How do you handle class rarity on the algorithmic level? It's basically like we said, it's just choosing which algorithm you want to use. There's many different algorithms you can choose from, but the three that were used in the journal that was assigned to me were random forest, which is essentially a group of decision trees with random data points, using random data points. The second one is gradient boost forest, which is essentially you're building one tree at a time sequentially, but every tree optimizes on the previous tree's error. So it's trying to reduce the error from the previous tree. And the last one is logistic regression, which is similar to linear regression, except for this one you're using a sigmoid function to generate the class possibilities, and you're setting your threshold to separate the two. Here is here is a graphic of random forest, just so it's clear. Basically, you take one entire data set and you break it into subsets, but your subsets are randomly chose. And using random subsets of features, you split into a tree. So this is your first tree, your second tree, and your nth tree. You get the prediction of each tree, and then you use majority voting to make your prediction of each class. Okay, here's an example of gradient boost forest, just so it's clear. Now you get your data set. You use your full data set, and you make one decision tree. You get your prediction, but you run all your information from this data tree into your next. You repeat it, and you try to reduce your residual error, and you're just optimizing as you go. Now you put all these trees together, and you make your random forest. Well, not random forest, but your gradient boost forest here. Won't get into logistic regression because we covered that extensively in class. In conclusion, you can handle imbalanced data class rarity wherever you choose on a external data pre-processing data level, internally in the algorithmic level, or hybrid using both methods. You just choose whichever method is the best for your application. Different problems have different properties, different statistical properties, which require a more tactical approach. Now, to dive into that, now let's say you have big data, you have millions upon millions of data points, then you might want to, if you're handling this on a data level, then you might want to choose to undersample. Now, if you have a small data set with only a couple hundred, then you want your model to learn on as much information as possible. Then you can't afford to lose any information. You want to oversample. Uh, generating synthetic or using smoke is always a good idea, but keep in mind that it's more sensitive to overfitting if you introduce noise. So when you have data sets, data points overlapping each other, then you can generate some noise and cause overfitting. Now, on the algorithmic level, is pretty much just whichever algorithm you feel handles class rarity the best is the one that you want to proceed with. Now, my paper was just using these algorithms to demonstrate that the more imbalanced your data set is, then the worse your algorithm is going to perform. Doesn't matter which one you choose, the worse they're going to perform, the more imbalanced the data set is. So, with that being said, going forward in the future works, it could be beneficial to look at hybrid approaches in tackling imbalanced data. Okay, now with that being said, that is all for my presentation. It's been an honor. I hope that next semester is just as good as this semester. Carry on, classmates.